Now that you've completed the quiz, it's clear that the bottom expression is a valid approach to grow the array. Let's finish adding all the data for a second student and then add a third one too. So to add the student, we proceed as we learned in the quiz. Recapping, student is a 1-by-1 struct. Therefore, student2 is the non-existent second element. Assigning a name to the second element will grow the array. We do so and follow with the student ID and the scores. We can add the third student in an identical fashion. At this point, let's verify the properties. The class of student is struct. The size of student is 1/3. And the number of elements in student is, of course, 3. Remember that size and number of elements refer to the object student, but not to the contents of its fields. In this example, we grew the array by assigning beyond its boundaries. When it was 1-by-1, we assigned to the second element, growing the array to be 1/2. After that, we assigned to the third element, growing it to be 1/3. This is an acceptable approach, but it can be inefficient for large arrays. We saw some dramatic inefficiencies in this in some earlier exercises with large double arrays. The same thing holds for struct arrays. You've probably experienced the Matlab editor making recommendations to you about the inefficiencies of changing the size of arrays in functions. The point to remember is that assigning beyond boundaries is usually not good practice. It's better to pre-allocate to the correct dimension and fill. For comparison, let's make up an array consisting of a single double. The size of A is obviously 1-by-1. What happens if we grow A by assigning beyond its boundaries? Let's assign something to the 3-4 entry of A. Notice that the array grows properly to 3/4, and all the unassigned elements which have been introduced by the growth are simply initialized to 0. What happens to the unassigned fields when we grow a struct? Student already exists, and it's the 1-by-1 struct consisting of Fred. Let's grow it to a 1-by-2 struct by adding Esme to the name field of the second element. The size of student is now 1/2. What are the values of the SID and scores in that second student? Here we see they are empty. That's analogous to the zeros which were filled in when we grew a double array beyond its dimension. Take time to verify the other behavior that we saw in the slides. The struct function is a general purpose command to create struct arrays. If A, B, and C are cell arrays of the same dimension, n1/n2, then this command creates an n1/n2 struct array S. S has 3 fields given by the names listed. The values of the fields are given by the cell arrays. For any element of S, the value of field 1 is the corresponding contents of the elements of A. Similarly for field 2 and B, and field 3 and C. How does this apply to pre-allocating a struct array? Let's consider the task of creating a 200/100 struct array with 3 fields, empty matrices for all the fields for all elements in the struct array. We can start by using the cell command to create a 200/100 cell array. Remember that with the cell command, the contents of each of these cells will be empty doubles. Then we use the construction above, listing the field names and repeating D for each of the cell arrays. This creates a struct of dimension 200/100. There will be 3 fields, and the value of every field at every element will be an empty array. That's what we call pre-allocating a struct array. Now that it's allocated, we can assign a value to the second field in the 9712 entry of the array as shown.